Okay, so today is a review day, practice, just to make sure that I know this is kind of complicated material, to make sure that things are sinking in a little bit. So I have quite a few questions that, quite a few questions that we can go through, and I can always come up with more. So this is mostly for you to refer back to, and I would say the vast majority of it is the concept side of things. So there has been this storyline going throughout this chapter. The key point that we come to is the fact that the electron started to be modeled not only as having particle-like character, but as having wave character as well, okay? So this wave-particle duality of the electron. Now that happened to light too. We thought of it only as a wave, then we started to think of it as a particle and landed on this kind of, we have to think of it both ways sometimes, but really the end result that we care the most about is the model of quantum mechanics that's based off of this idea of viewing the electron not just as a single particle, but having wave-like properties. Like when you get to higher levels of quantum mechanics, you can calculate the wavelength of an electron, okay? So there is very close tie between energy in the form of light as there is to an electron. Even though an electron has a visible mass and light doesn't really, it almost behaves like it does, okay? So that's like the storyline that goes through this. The calculations that we did early on were calculating between wavelength or frequency and getting us to energy. Okay, so if you're ever given the energy associated with a particle of light, a photon, you can track that back to its wavelength or vice versa. And we also had this calculation, which gave us the energy associated with a particular transition in the Bohr model. Now, I did change this in your, I don't want to harp on this because it is like such a minor thing. Let me just put it in conceptual context. If you are releasing energy, you will see that energy is listed as negative. It just means it's being released. There isn't negative energy. There isn't opposite energy. There's just negative in the sense that it's being released rather than absorbed, okay? You're never going to report a wavelength or a frequency as negative, though. I just won't give you a negative or positive in those. I'll just give you the straight energy or straight wavelength or whatever, okay? All right, so then we got to quantum numbers, which basically told us about a particular region of space where an electron was likely to be found, okay? So in the Bohr model, we said that there were these restrictions on the energy associated with an electron. So an electron could be here or here or here, but it couldn't be in the middle, all right? So it had a specific energy, you know, like we could give these random numbers, 100, 200, 250. Like we could give them exact numbers and say an electron will not have an energy of 75 or 26 or whatever. It can only have these designated energies. That came out of the Bohr model, and that was an important finding of the Bohr model. But what the quantum mechanical model gave us was a better understanding of what those energies were. So we end up with the energy levels are still there. I'm going to show them a little closer to each other than maybe we do. We show them in this like staggered form sometimes, which is fine, but I don't want it to imply something it doesn't. Okay, so there are still these energy levels. It's just that they're maybe broken down a little bit more than we realized. So in Bohr's model, we had the n equals 1 and n equals 2 and n equals 3, and that's still true. It's just there's kind of subdivisions of those energy levels that are still restricted energies that the electrons can have, But now they're restricted not only by the distance out from the nucleus, but by the shape of that orbital itself. And if you're getting lost at all during this point, just keep remembering that an orbital is a region of space where the electron is most likely to be found. Okay, so we define these regions of space and say the electron is going to be in this region. Okay, and that region defines its energy. So at the beginning, we have the 1s orbital, so n equals 1, and the shape is a sphere. Then we have the 2s, n equals 2. Again, the 1 and the 2 and the 3 are like outer edges, how far they are out from the nucleus. So if, when we get to the n equals 3s, there's 3 different shapes. They all kind of end at a particular distance out from the nucleus. The letter tells us what shape they are. And remember, that is associated with the quantum number L. So n is the distance out from the nucleus. L is the shape. We'll just put that up here. And to make it a little easier to talk about it, we give it a letter. S, P, D, and F. It has to do something with the emission spectra lines and how they looked before they had good resolution. They called them sharp, principal, diffused, and fundamental. So it doesn't really have any meaning anymore, but that's where they came from. There was an actual reason. There usually is. Okay, so we had the 3s, the 3p, and the 3d, and hopefully you guys see that every time we go up an n level, we add another shape. So when we go to the 4th one, we've got 4s. Now at this point, I will tell you the energy gets weird, so I'm going to write a energy question mark. We're going to talk about that in the beginning of chapter 9. So don't hold me to the way I'm drawing this right this second, but I want you to see the difference between 1, 2, 3, and 4. Okay? So then we get the 4p, the 4d, and the 4f. Okay? So every time we go up an n, we get another shape of orbital. And every time we go one shape higher, we get another set of orbitals. So in the S, we only have 1. In the P, we have 3. In the D, we have 5. And in the F, we have 7. Okay, we didn't make this up. This is what the numbers that resulted from these equations showed. And the equations were consistent with experimental results. And so that was like how we verified it. But we didn't make up the fact that when you get to the 4th level out in energy, there are 7 different locations and energies where the electrons can be. Well, there's more than 7. There's 7 in the F, right? There's 7 additional ones. Okay, so the number of orbitals in a given, we call these subshells. When we have the 1s, the 2s, the 2p, those are subshells. So the orbitals, how many there are in a given subshell, that corresponds to how many m sub l values there are. So remember, m sub l comes in a range. So if we're talking about the p orbitals, where l is 1, then we have 3 m sub l values. And that's, like I said before, we don't care so much about what the actual values are, like a little bit. But in the end, what we really pay most attention to is the fact that there are 3 of them for the p subshells, and there are 5 of them for the d subshells. The reason we don't care about their values that much is because they're all the same energy. So you can see when I've drawn like the 3D, they're higher in the 3p, but all 5 of them are the same energy. And then the last one, the m sub s, designates is the electron spin up or spin down, positive 1/2 or negative 1/2. So the first 3 tell you what orbital it's in. Well, let me start earlier. The first one tells you what shell it's in, how far out from the nucleus it is. The second one tells you the shape of the orbital. The third one defines the orbital itself. So in the 3p subshell, there are 3 orbitals. If I give you all 3 quantum numbers, 3p, which is L of 1, and also the m sub L value, negative 1 or 0 or positive 1, then I'm designating a specific orbital within that subshell, okay? So if you want to talk about a specific orbital, you have to give all 3 of those quantum numbers. Then the m sub s gives you which electron you're talking about in that orbital, okay? All right, so let's use this and do some practice here, okay? So start with these 2. List what n can be, which one's lowest in energy, and which one is closest to the nucleus. Take maybe a minute or so, and then we'll talk about that. Okay, so let me give you like how these would be worded as a test question, because any of these I could turn into a test question, okay? So maybe I would say select which list shows the lowest 3 n levels, and that would kind of, lowest energy n levels, and that would kind of encompass 2 of these. So I could say 0, 1, and 2. I could say 1, 2, and 3, or I could say negative 1, 0, and positive 1. Okay, so let me restate the question. Select which of these shows the lowest 3 energy n levels. Okay, so it's this one. There's no 0 with the principal energy level, the principal quantum number. It starts at 1 and just can be any integer after that. And it has no restrictions as far as like when we get to the L values, you know, you can only have an L value of 0 at n equals 1. At n equals 2, you can have an L value of 0 or 1. So like there's no restrictions to the n values. They're kind of independent of anything else. The lowest energy one is 1, Okay, so it starts at 1 is the lowest energy, and that is also the one that's closest to the nucleus. Whatever is closest to the nucleus is going to have the lowest potential energy. And that's really all we care about with the electrons at this point. We're not worried about their motion, their kinetic energy, because that's not going to change a whole lot. We're just worried about their potential energy, meaning the closer they can get to the nucleus, the lower in energy they are. Yep. So I was saying I was trying to create a test question that was multiple choice. So this would show the lowest energy values of N, the first 3 or lowest 3 energy values of N. Because you can't have a 0 and you certainly can't have negatives for N values. Okay, so this one, for each N value, and I'm going to write this 1 at the bottom. Am I going to do that? No, I'm not going to do that. Okay, so N equals 1, N equals 2. Maybe I should just write N above and make it a chart. And then I can do that for L. 3 and 4. So I want you to tell me the L values, the number, and then also the letter that you see at N equals 1, 2, 3, and 4. So take maybe 2 minutes to do that one. We use this term allowed values a lot. You're going to see that. Allowed values for L. Okay, so when it says allowed values, you want to think back to these rules about, for example, L is allowed to be a range of 0 through N minus 1. Okay, so when you think of allowed values, think of that rule and then do it for the specific N value. So for an N value of 1, a range of 0 through 1 minus 1, or 0. So the only allowed value for N equals 1 for L is 0. For N equals 2, 0 through 2 minus 1, or 0 through 1. So 0 and 1. For N equals 3, 0 through 3 minus 1, or 2. So 1, 0, 1, and 2. And then for 4, 0, 1, 2, and 3. So what I'm hoping is that by the end of this, you are conceptually understanding the storyline that goes throughout chapter 8, this change in how we viewed light that led to a change in how we viewed the electron, that led to this idea of the electron only being allowed certain energies. That was verified by the emission spectra. The initial model was developed by Bohr, but that only looked at an orbit, a particular distance out from the nucleus. And once we started modeling the electron like a wave, we could predict a region of space that had a particular energy, so it was still consistent with the emission spectra. And the quantum numbers are the results of those equations, and they define where that region of space is. So like if you had an element with 5 electrons, you would have 5 different mathematical functions that would all define those 5 electrons. And we could actually, I think this is probably a question. Oh, come on. I'm just going to do it now because I don't see it on there. Okay, so let's say we have, what is that, boron? Lithium, I think it is. Okay, so boron, 5 electrons. We would have 5 different equations to define each of those electrons. So I'm going to label them as like electron 1, electron 2, electron 3, electron 4, and electron 5. And obviously I'm not going to like show you the equation that was used. Instead, I'm going to show you the results of the equation. Okay? Electrons are always going to tend to the lowest potential energy. So like I'm going to say that those first 2 electrons are both in the 1s subshell. I should have made this a table again. Okay, so while you're writing that down, I'll go put these as a table up top instead of rewriting N equals L equals every single time. Okay, so the first electron of those 5, these would be the results of that equation that told us the energy of that particular electron. The second electron is going to be in the same orbital, but it's just going to have a different spin. And this is what I mean by like every electron has a unique set of 4. Obviously, they're going to have some that are the same, but they're never going to have 4 that are identical. There's only 1 orbital in the first energy level. So with that third electron, I have to go up to the second energy level. Still an s orbital. There's only 1 s orbital, so its m sub l is 0. And the next 2 electrons will be in that orbital. So 2, 0, 0 plus 1/2, 2, 0, 0 minus 1/2. And I'm just starting at the lowest energy ones and working my way up. How do I know that they're lowest in energy? The n should always be a lower number, and the l should be a lower number. So like 1s is lower in energy than 2s, and 2s is lower in energy than 2p, which is the next one we get to. Now, here's a question. Does the m sub l matter if it's -1, 0, or +1? No, it doesn't, because those are all equal in energy. But we know it's one of those. It's not all 3 of those. So we're going to kind of arbitrarily pick. It doesn't actually matter as long as it's one of those 3, -1, 0, or +1. Usually, I don't even know that this is convention everywhere. I will start with the negatives and go to the positive. It is convention, though, that if you only have 1 electron in an orbital, it's plus 1/2. So you start with the plus 1/2 and then you go to minus 1/2. Now, technically, if you're not in a magnetic field, those aren't detectable at all, so it doesn't really matter. Same thing with the M sub L. You can differentiate those within a magnetic field, but not in just like everyday life. Okay, so those would be the set of 4 quantum numbers for the lowest energy 5 electrons, really in any atom. Those would be the first 5 electrons. Now, I said boron because it only has 5 electrons, but like this would be the lowest energy 5 electrons for lead as well. Even though lead has 26 of them, these would be its first 5. Yeah?
How do you know the spin?
So the spin is always plus 1/2 or minus 1/2. In a given orbital, you have to have one of each. So let me draw this, because I think sometimes seeing a visual representation makes it a little more easy to understand. So 1, 2, 3, 4, 5. So what I was saying about this one here, so if it's pointed up, it's plus 1/2. So this one here, we just always start by saying it's positive. And then if we add a second one, we'll say it's negative. So this is going to come up in chapter 9. But let's see, boron, carbon, nitrogen. Let's do oxygen. So oxygen has 8 electrons. And if you can see like how I'm filling these in, this should help you understand like how we know when to call it plus 1/2 and when to call it minus 1/2. So I fill in the 1s first. So it's not going to go up to the 2s before you pair up the electrons in that orbital because it wants to stay lowest energy possible. The 2s is lower in energy than the 2p subshell. So again, I'm going to put 2 electrons in there before I do anything else. And this is that first 4 lines that we've written. So I'm going to highlight as I go. N equals 1, L equals 0, M sub L equals 0. 1's plus 1/2, 1's minus 1/2. It'll always be one of those. 2s orbital, 1's plus 1/2, 1's minus 1/2. You haven't seen this before, so don't stress if I'm doing this and you're like, whoa, wait. We're going to see it by Wednesday probably, the beginning of chapter 9. When we do, so if we're doing carbon for a total of 8 electrons, when we fill them in the 2p orbitals, we fill them one at a time, all being plus 1/2, and then we go back and pair them. So 8 electrons would look like this. Because electrons repel each other, so they're not going to pair up until they have to. Now, by have to, I mean they want to pair up in 2s rather than going up in energy to the 2p, but they aren't going to pair up in the 2p until there's not another 2p. Like you will not see this. This would not be the lowest energy state. Because you have another orbital of that same energy, it's not going to pair up if it doesn't have to. So this is what oxygen would look like. We're really veering into chapter 9 here, just so you know. It's just, this stuff is like, if we could just brain dump it all at once, I think it would be better than trying to spread it out and then just keep doing the same brain dump for 4 days straight. But it just doesn't work like that. Because, you know, we don't meet for 3 hours at a time. I'm not going to go through all of the quantum numbers for these 8 electrons. If we have time at the end, we could do that, but right now, not. Yes, but it's a range because there could be multiple of them. So n minus 1 for 1 is 0, right? N minus 1 for 2 could be 0 or 1. So I have one orbital right? Because 2 electrons per orbital. So I have 1 orbital where it's 0, or 1 subshell is a better way to think of it. So let me add those titles up here. So this is the shell. I was trying to do that in a different color. This is the shell. Putting N and L together would be the subshell, and then putting all 3 of them together would be the orbital. So this isn't really, let me do this. Shell is N, subshell is N and L, orbital is N, L, and M sub L. So when we say it's N minus 1, it's 0 through N minus 1. So it could be 0 or it could be 1. And when we go up to 3, it could be 0, it could be 1, it could be 2. Yeah.
How did you get those? How'd you get the first 2 zeros and the second or third?
Because I always want to hit the lowest energy things first. So when we get all the way to the end of chapter 9, the easiest way, I think, for you to do this is to first draw yourself the picture and then go from there. So like if I drew this picture first, I could look at these 2 electrons and say those are lowest in energy. They have an N of 1, they have an L of 0, and an M sub L of 0. One has an M sub S of plus 1/2, one has an M sub S of minus 1/2. And then I'd like check off those 2. Then I'd go to the next 2 that were lowest in energy, and I'd say, okay, that one has an N of 2, L of 0, M sub L of 0. And if you want to label the M sub L's, you can. Remember, if there's only 1 of them, it's 0. If there's 3 of them, it's -1, 0, and +1. If there's 5 of them, it's -2, -1, 0, +1, +2, and so forth. So I think once you get used to doing it as, what these are called orbital diagrams, once you get used to doing as that, the other stuff, I think it's a visual thing, and maybe not everybody is visual, but I think that's probably the easiest place, at least for me, to start and then talk about the quantum numbers. Yeah.
So then on the chart that we made below, would the first 2 rows be the 1s?
Yes.
And then the second 2 are the 2s?
Yep. So remember, S is 0.
Yeah.
So, yep. So these, 1, meaning N equals 1, S, meaning L equals 0. And then the next 2, N of 2, L of 0. And then the final one, which could have as many, this subshell could have as many as 6 electrons total, and that would be N of 2, L of 1, or P. And just to clarify, I'll do it like this so that you remember that designation comes from the N and the L. So like we say there are 6 electrons in the 2p subshell. That's because there are 3 orbitals in that subshell, each orbital holding 2 electrons. At the end of class last time, let's see if I can find it, we started looking at this. This is what mentally you're gonna work out so that you don't have to see this, like you don't have to be given this. You're going to be able to draw that yourself based on the rules, the allowed values that we just said, like N is 0, 1, 2, etc. L is the range, 0 through N minus 1. M sub L is -L through +L. So if you just use those 3 rules, you could actually come out with this entire diagram. I guess the only other thing you would have to remember is that as N increases, or let's write this a different way. Energy increases as N increases and as L increases. So 1s comes first because it's the lowest n. 2s comes next because it's the lowest n and the lowest L of the two possibilities. Then comes 2p. Then 3s, 3p, 3d. But those are the only two that affect energy. M sub L does not affect energy. That's why when you draw the 2p, you draw them like horizontally in the same direction, because we're saying that this is an energy scale. Starting at the bottom and working our way up, things are getting higher and higher in energy. Was that a hand? No? Okay. All right, let's go back to a couple of these practices. Okay, so we just said this. When you combine N and L, this is the next one, right? Yep. When you combine N and L, this is called a subshell or sublevel, and each one has a different energy. This one says that we want to label the M sub L values. So I want you to show me each sublevel through N equals 4, and then tell me the M sub L value for each of those that are possible in each of those sublevels. So you could draw them out, and I'll maybe do the first one or two. You could either draw them out, or you could just write them down. So tell me the sublevel in one column, and then tell me the possible M sub L values in the other column. So I'll give you the first one. 1s is the first sublevel. The possible M sub L value there is just 0. Look at me, I have an attendance sheet for today and everything. What is today though? Okay, where are your pens? Oh, I'm totally gonna run out of room there. Try to squeeze them in here. Okay, so I'll finish the fourth one in a second. If you want to check these answers, though, feel free. So sublevel is N and L, but for the L, we use the letter. And then the M sub L, remember, is a range of negative L through positive L. So we need to look at what L is. We don't actually worry at this point about what N is. We're just looking at L. So an L of 0, which is what S means, the only possible M sub L is 0. P is an L of 1, so that could be negative 1, 0, or positive 1. D is an L of 2, so negative 2, negative 1, 0, positive 1, and positive 2. So you see this is repeating, right? Like this set, and then we add another set, right? Because we're adding another type or another shape of orbital every time we go up an n level. So then finally, F is an L of 3. So negative 3, negative 2, negative 1, 0, positive 1, positive 2, positive 3. Like I said, all of this practice is helping you to establish in your head what the possible orbitals are, and then eventually knowing the energy associated with those orbitals. So the ultimate picture you're going to be drawing in your head is that chart from the end of last class. This one here. That's what you're ultimately working towards, is getting that chart in your head. And to be honest, the periodic table is going to be very useful in solidifying the order of energy that those orbitals will go in. So that's also part of chapter 9. Okay, give this next one a try. I'll scroll back to the previous page in a second once everyone sees which question we're on, so that if you haven't quite written that all down. Okay, so we actually did this before. For the 3D subshell, we want to know how many M sub L values, how many of them are there. So D is an L of 2, which means M sub L can be negative 2, negative 1, 0, positive 1, or positive 2. So a total of 5 M sub L values. Not what are the M sub L values, but how many of them are there. Because what this is really telling us is that in the 3D subshell, there are 5 orbitals. And in each of those orbitals, you can have 2 electrons, so a total of 10 electrons possible in the 3D subshell. Is it possible to have an L of 5 when n equals 5? No, because we said that L should be 0 through n minus 1. So your top number for L is always going to be 1 less than whatever the n value is. So an n of 5 could have an L of 0, 1, 2, 3, or 4. Now, we haven't talked about what an L of 4, what the letter is or what it looks like. It's still good to know that that's an allowed L value and that L equals 5 wouldn't be an allowed L value for n equals 5. Let's skip the next one and go to the last page. So just a minute or so, and then I'll go through it. Okay, so L of 2 is D, so the sublevel designation is 5D. The possible M sub L values, -2, -1, 0, 1, and 2. This is how many orbitals there are. How many orbitals are in this sublevel? There are 5 total. And then it wants us to give all 3 of those quantum numbers for those 5 orbitals. Okay, well, it's the same sublevel every time. So 5 and 2 for all 5 orbitals. And it's just the M sub L that changes. -2, -1, 0, 1, and 2. Again, because all 3 of these, that's what defines an orbital. Okay, so we're going to be doing the same thing. We're just building on the same thing in Chapter 9. And if anything, I think it'll help you to remember it better as we do more practice and kind of add some more detail to it. Okay, I'll see you guys on Wednesday.